Calculus, limits. That's what we're doing today. Limits will be split up into 3 different parts. We're going to do part 1 first. Okay. Now, we're going to take a look at this rational function, and we've seen something like this before in Math 11 already. This is a rational function, x squared minus 9 over x minus 3. Now, with rational functions, we know they're defined for all values of x except when, and if you're thinking, yes, the denominator equals to 0, that's correct. So remember your NPVs, where you make the denominator equal to 0. So of course, in this case, the function is defined for all x, except when x equals to 3. Okay. Now, the question I have for you is, what is the y value when x approaches to? So I'm not saying equals to, but approaches to, meaning getting closer and closer to, but not equal to the number 4. Well, we can do this on a graph if we want. I'm going to ask you to bring out your graphing calculator. Let's go ahead and actually graph out this function. Y equals 2. Put a bracket around this. X squared minus 9 divided by x minus 3. Okay? I'd like you to graph. Get a nice line. If we were to make a table of values, which I will do now, table, let's go back to table set. I'm going to start at, let's say, about 2, increment it by 0.1. Let's do automatic, and then let's go to our table. So you see, my question to you is, what happens when we get closer and closer to 4? What does the y value get closer and closer to? Looks like it gets closer and closer to 7, right? 6.9, 7.1, gets closer to 7. Now notice in this case, when x equals to 4, what am I doing? When x equals to 4, the y value is also 7, okay? But what happens to the value of f of x, okay, as x approaches 3? Now we know it doesn't equal to 3, so if I scroll up here, you see at 3, it says it's an error. But what happens when it gets closer and closer to 3? So what I'd like us to do is make a table of values, okay? We've got 2.9 already, so 2.9, and we know that's 5.9, right? We see that. And at 3.1, we know it's 6.1. Well, let's see if we can get even closer and closer to 3. Okay. I'm going to change my table set now. Let's make it 2.9. I'm going to increase that by like 0.01. Okay. Let's get a table now. So something like 2.95. You see what I have here? 5.95. I'm going to do a few more. How about 2.97? Five 5.97. Well, you might be thinking, I want to get even closer. How about 2.99? That's 5.99. Notice still at 3 it's an error, but at 3.01, 6.01. So can you see how it converges on a particular number? What does it look like it approaches? Not equals to, but approach. Approaches, if you said 6, you're correct. So despite there being an error at 3, if I use the word approaches, that means getting closer and closer to 3. So at values like 2.99 or 3.01, the y value seems to get closer and closer to 6. So the value of f of x, which equals to 6 in this case, as x approaches to 3. Now there's a notation that we use for calculus to describe what I just said. And we use this thing called the limit. The limit as x approaches to 3 of the function f of x is equal to 6. So let me write this in words. The limit as x approaches to 3 of the function f of x is 6. So in essence, what I'm saying is the y value seems to get closer and closer to 6 when x gets closer and closer to 3. There are something called one-sided limits that we should take a look at too. Okay, the left-hand limit. So this is the limit when you approach x from the left. So if you look at our previous example of the function x squared minus 9 over x minus 3, the calculus notation would be this: x approach to, and once again that's arrow, 3, but from the left use a minus sign of f of x. So those will be values like these ones, 2.99, 2.77, all those. Okay. Whereas if I'm curious about the right-hand limit, that's the limit when you approach x from the right. In this particular example, from the right would be these values, 3.01. And to show you the notation for the limit, it'd be the limit as x approaches to 3, and you put a plus sign, f of x. Okay. Now we have these one-sided limits from the left and from the right, but in order for a limit at a value of x, okay, to exist, we need the left limit to equal to the right limit. Okay, so the left-hand limit must equal to the right-hand limit. And the calculus notation here is that the limit, for example, in this case, from the left must equal the limit from the right in order for the limit at that particular value to exist. Exist meaning there's an answer. Okay? So what I'd like us to do now is look at some examples and see if we can determine the following limits. Okay? We'll do some limits from the left, we'll also do some from the right, and if you're not too sure, let's see if we can graph these out so we get a better understanding by looking at the visual picture. Okay? The first one I think is pretty easy to graph out, as I hope it is. It's a line with the y-intercept at 2, and it seems like the slope goes downward. So here's what we have. Right, y-intercept of 2, slope equals to -1. Now I'm asking you, in this case, find the following limits. The limit as x approaches to 1 from the left, so that'll be me traveling from the left going towards 1, and notice what the y value gets closer and closer to. I believe it's 1. And then as x approaches to 1 from the right, seems like I come from the right, and as I come from the right, it seems like it's also approaching the number 1. So before I say what happens at the limit at 1, can you see how the limit from the left and the limit from the right equal each other? And because they equal each other, then you know that the limit at that particular value exists, and the answer was also the same, which is 1. Okay? Now, what about b? This is the reciprocal function. You guys should remember that from grade 11. Remember, the reciprocal function is you take this line, and then wherever it crosses the x-axis, you have an asymptote, big dots at 1 and -1, and so you have these crazy reciprocal curves. Remember, in this case now, I'm asking for what's the limit as x approaches to 0 from the left. So from 0 from the left, I'm going this way, and it's going down, down, down towards -infinity. Well, if I ask you to find the limit as x approaches to 0 from the right, yep, it goes up, 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 up to positive infinity. So in this case, what would be the limit at 0? Well, remember our definition from above. For a limit to exist, we need the left to be equal to the right. And so therefore, is the left equal to the right? No. And then you get that famous saying from Mean Girls, the limit does not exist. And the notation that some people use is D, N, E. Okay? Good old Mean Girls. Okay, part C. Oh, this is an interesting sketch. Absolute values. Remember an absolute value function as a piecewise function? Remember that becomes positive x if x is bigger than 0, negative x if x is less than 0. So if you think about this function, you've actually got two parts. You've got positive x over x if x is greater than or equal to 0. You've got here negative x over x if x is less than 0. So if you think about this, you've got the piecewise function of 1 if x is greater than or equal to 0, or negative 1 if x is less than 0. Okay? Quick sketch if you want. I'll quickly do it here. Positive 1, whee! Negative 1, whee! Open dot. So at 0 from the left, you're coming this way. The answer seems to be negative 1. Coming from the right, it's this way at positive 1. And therefore your limit, of course, once again, it's a does not exist. Okay, I'm going to ask you to try the next piecewise function on your own. Okay, let's see if you can figure that one out, please. So I think that's the piecewise function, right? Goes through, so that's 2. And this is 2, and that must be 3. That looks ugly. Okay, what's the limit from the left? Coming from the left, it looks like it's equal to 1. Coming from the right, it looks like it equals to, now even though it's an open dot, it's still approaching that value, so it's 2. And once again, they're different, so the limit at 1 does not exist. Okay, let's turn the page. Okay, I think we've actually done 2a already, so done. See previous page. But I'd like you to at least try 1b. So for this function, see if you can sketch the graph and then find the limits in this case. Okay. Remember how to graph out reciprocals. Y equals x squared. Where it crosses the x-axis, vertical asymptote, 1, 1. Big becomes small, small become big. Now you have to graph 1 over x squared. Okay, see if you can find the limits here from the left. Whee! Positive infinity. From the right, whee! Positive infinity. So if they're both equal to positive infinity, what's the limit as x approaches to 0? And if you answered positive infinity, you are correct. Okay. Now be careful when f of x has an infinite limit as x approaches to a from the right or from the left. The graph of the function gets closer and closer to the vertical line, and I'll say the vertical line x equals to a as x approaches the value of a, right? The vertical line in this example here, that vertical line is x equal to 0. Okay? What do we call these vertical dotted lines? You've seen them before. It's called vertical. And if you remember that word asymptote, you are correct. Okay, a vertical asymptote of the graph. So in each of these examples now, I'd like you just to look at the visual, the graph, and see if you can find the limits of these things. Okay? And then once you do that, then you've had a pretty good understanding of the beginning parts of limits. All right? So let's do 1 together, and then I'll let you try 2 and 3 on your own. Okay? The limit as x approaches to -2 from the right. See that plus sign there is from the right. So here's -2 coming from the right. That's like this part. It gets closer and closer to, and remember you're looking for the y value. So the y value here is 0. Okay. If you're looking at now the next one, x approach to 0 from the left, that means I'm getting closer and closer to 0, but coming from the left, and you see that it's approaching the y value of 2. The next one over here, I'm looking for x approaches to 0 from the right. So here's 0, but I'm coming from the right, so I'm coming down this way. Seems to be approaching number 1, even though it's not equal to 1 at 0. And so therefore now looking at the two previous things, what is the limit at 0 if the limit from the left and the right do not equal each other? dne. Okay. And the limit as x approaches to 2 from the left. Well, in this case, I'm looking at here, getting closer and closer to 2 from the left. Looks like the value of 3. Okay, even though it's an empty dot, right? I'm getting closer and closer to 3. Not 2, but closer and closer to 3. Similarly, x approaches to 2 from the right, coming this way. I'm not going down there, but I'm staying up here, so that's still 3. And then if I asked you for the limit as x approaches to 2, because the 2 previously from the left and from the right both equal to 3, this also must equal to 3. And finally, the last one, x approaches to 4 from the left. That's this way from the left. Looks like I'm getting closer to the value of 4. By the way, note just a really quick thing here. What's f of 2? Meaning, what is the y value when x equals to 2? And the answer is 2. You're right. So notice when I compare this with this, they don't have to be the same. The limit as x approaches to 2, meaning what happens when you get closer and closer to 2, is equal to 3. Yet, when I'm actually at 2, the y value is 2. They don't have to be the same. Okay? The limit and the y value at that point does not necessarily have to be the same. Okay. You take a look at number 2 now, please. Okay? And I want you to try that on your own. Pause the tape now. Okay, once you've done 2, try 3. All right, so there you go. There are the answers to 2 and 3. Now notice here, I've got a little note down here. The actual value of the function at these points has nothing to do with the one-sided limits. So what I mean by that is look in this case here. Okay. Notice in example number 2, if I asked you for the one-sided limits as x approaches to -1 from the left, we actually did this, right? -1 from the left, yeah, that's 2. The limit as x approaches to -1 from the right, well, that's 1. But notice the value at -1 is equal to 1.5. So once again, the value has nothing to do with the one-sided limits. They can be the same, but in these breaking points here where there's a break in the graph, they're usually not the same. Okay, just want to keep that in mind. All right, you go ahead and try the rest, please.